When students first start organic chemistry, one of the most confusing things is that the same compound can seem to be written in lots of different ways. Sometimes you might see a molecular formula, sometimes a structural formula, and sometimes a displayed formula. Then, suddenly, there are skeletal formulae that don't even seem to show all the atoms. But all of these representations exist for a reason. Organic chemistry contains an enormous number of compounds, and chemists need different ways of communicating information about them. In this lesson, we're going to look at the reason why carbon can form so many different compounds, before exploring why each of the different chemical formulae exist, what information they give us, and when chemists would choose to use them. And if you'd like to follow along with this lesson, there's a free Learn Pack containing guided notes, worked examples, and practice questions linked below. Before we can understand why organic chemists use so many different ways of representing compounds, we first need to understand exactly what organic chemistry is. The term organic refers to living things, so organic chemistry is essentially the chemistry of living organisms. However, life on Earth, as far as we know, is entirely based on carbon, and so organic chemistry is actually the study of carbon-based compounds. For a long time, scientists believed that the carbon-containing compounds found inside of organic material could only be created by living things. Today, we know that isn't true. Carbon-containing compounds can be synthesized in laboratories and factories, and this is why organic chemistry now includes everything from pharmaceuticals and fuels to plastics and synthetic materials. But what makes carbon special that it ever deserved its own branch of chemistry? After all, the periodic table contains over 100 different elements. Well, this is where we can explore the unique properties of carbon, properties that allow it to form over 20 million different compounds, more than those formed by every other element on the periodic table combined. Carbon atoms have 4 electrons in their outermost shell, and this means that they can form 4 covalent bonds. And this allows carbon to connect to multiple atoms at the same time and create a huge variety of different structures. However, where carbon really begins to stand out is the fact that it can form very strong covalent bonds with other carbon atoms. This allows it to create stable chains and rings that can contain dozens, hundreds, or even thousands of carbon atoms. But carbon atoms can also form single bonds, double bonds, and even triple bonds, either with itself or with atoms of other elements. Combine that with carbon's impressive ability to form stable chains, branched chains, and ring or cyclic structures, and you begin to form an almost unfathomable number of different molecules and compounds. So if carbon can form millions of different compounds, chemists need a reliable way of communicating exactly which compound they're talking about. And that's where chemical formulae come in. Different chemical formulae emphasize different characteristics or features of organic compounds. And there isn't one single representation that is ideal for every purpose. As a consequence, there are a number of ways scientists represent organic compounds. So let's begin with perhaps the simplest way of representing an organic compound, the molecular formula. Now, the definition of a molecular formula is one of those things that often comes up in exams, so it's worth making sure you know it accurately. The molecular formula gives the actual number of atoms of each element in a molecule. For example, methane has the molecular formula CH4. This tells us that each molecule contains 1 carbon atom and 4 hydrogen atoms. Similarly, ethane has the molecular formula C2H6, meaning each molecule contains 2 carbon atoms and 6 hydrogen atoms. And propane has the molecular formula C3H8, containing 3 carbon atoms and 8 hydrogen atoms. As well as being asked to define what a molecular formula is, you could also be asked to work out or deduce a substance's molecular formula, and this is simple enough to do. To work out a molecular formula, simply count up the number of atoms of each element present in the molecule. For organic compounds, we conventionally write carbon first, then hydrogen, followed by any other elements present. Let's take a look at ethanoic acid as an example. Starting with carbon. Well, there are 2 of those, so I start my molecular formula with C2. Hydrogen, There's 4 of those in total. So now I've got C2H4, and finally I have 2 oxygen atoms. So my molecular formula becomes C2H4O2. So molecular formulae are actually very useful because they quickly tell us the composition of a molecule. We can immediately see how many atoms of each element are present without having to draw out the full structure. However, there is a significant limitation. Remember we said earlier that carbon can form an enormous number of different compounds. The problem is that a molecular formula only tells us how many atoms are present. It doesn't tell us anything about how those atoms are arranged. For example, the molecular formula C2H6O tells us that a molecule contains 2 carbon atoms, 6 hydrogen atoms, and 1 oxygen atom. But it doesn't tell us where that oxygen atom is located within the molecule, or even how the atoms are connected together. In fact, there are 2 completely different organic compounds with the molecular formula C2H6O. One of them is ethanol, the alcohol found in alcoholic drinks. The other is dimethyl ether, a compound used as a propellant in some aerosols. Both contain the exact same number of atoms of each element, but the atoms are connected in different ways, which gives them completely different structures and very different properties. So whilst molecular formulae are useful for showing the numbers of atoms present, they don't provide enough information for organic chemists to uniquely identify a compound, and that's why we need other ways of representing organic molecules. A second way of representing compounds is the empirical formula. Now once again, the definition here is important examinable content, so make sure you know it accurately. The empirical formula shows the simplest whole number ratio of atoms of each element in a compound. Notice that this is different to a molecular formula. A molecular formula tells us the actual number of atoms of each element present within a molecule, whereas an empirical formula only tells us the simplest ratio between those atoms. Let's look at some examples. Ethane has the molecular formula C2H6. If we were to simplify that ratio by dividing both numbers by 2, we get CH3. Therefore, the empirical formula of ethane is CH3. Similarly, hydrogen peroxide has the molecular formula H2O2. Dividing both numbers by 2 gives us HO, so HO is the empirical formula of hydrogen peroxide. Let's return to our earlier example of ethanoic acid. We saw that its molecular formula was C2H4O2. This can be simplified by dividing all of the numbers by 2, giving CH2O. Therefore, CH2O is the empirical formula of ethanoic acid. So whilst a molecular formula tells us the actual numbers of atoms present, an empirical formula only tells us the simplest ratio between them. But this creates an obvious problem. If I tell you that a compound has the empirical formula CH2O, do you know how many carbon atoms it contains? Well, not necessarily. It could contain 1 carbon atom, 2 carbon atoms, 3 carbon atoms, or many, many more. All we know is that for every carbon atom present, there are 2 hydrogen atoms and 1 oxygen atom. So empirical formulae contain even less information than a molecular formula. They don't tell us the actual numbers of atoms present, and they don't tell us anything about how those atoms are arranged. As a consequence, empirical formulae are generally not very useful for identifying or describing organic compounds. However, they are still extremely important in chemistry, because they can be determined experimentally and can help chemists work out the molecular formula for an unknown substance. For organic chemists, though, empirical formulae have significant limitations, which is why we often need more informative ways of representing compounds. So far, we've looked at molecular formulae and empirical formulae, both of which describe individual compounds in different ways. A general formula is different. A general formula is an algebraic formula that describes every member of a homologous series. Now don't worry too much if you're not entirely sure what a homologous series is yet. We'll be studying them in much more detail throughout the organic chemistry course. For now though, you can think of a homologous series as being a family of organic compounds that share similar structures and chemical properties. Remember we said earlier that carbon can form millions of different compounds? Well, rather than writing out the molecular formula for every compound individually, chemists noticed that many groups of compounds follow predictable patterns. And general formulae allow us to represent those patterns using a single algebraic expression. For example, let's consider the alkanes. Methane has the molecular formula CH4. Ethane has the molecular formula C2H6, propane's molecular formula is C3H8, and butane C4H10. At first glance, these all appear to be completely different formulae. However, if we look carefully, a pattern begins to emerge. Each successive alkane contains one additional carbon atom and two additional hydrogen atoms. More importantly, the number of hydrogen atoms is always equal to double the number of carbon atoms plus 2. And chemists can represent this pattern using the general formula CnH2n plus 2. The letter N simply represents the number of carbon atoms present in the molecule. So if N equals 1, the formula becomes CH4, which is methane. If N equals 2, the formula becomes C2H6, which is ethane, and if N equals 3, the formula becomes C3H8, which is propane, and so on. Rather than describing one specific compound, the general formula describes every alkane. And this makes general formulae extremely useful, because they allow us to identify patterns within an homologous series, as well as allowing us to deduce the molecular formulae of compounds we haven't encountered before. However, general formulae also have limitations. Just like molecular formulae, they don't tell us how atoms are arranged within a molecule. In fact, they actually tell us less about a specific compound because they aren't designed to describe individual substances at all. Instead, their purpose is to describe an entire family of compounds using a single algebraic expression. And that's what makes general formulae different from the representations we've looked at so far. But by this point, you may have noticed a recurring problem. None of the chemical formulae we've looked at actually show us how the atoms are arranged within each molecule. And that's a major issue in organic chemistry, because the way atoms are arranged within a molecule dictates exactly how and why they react. So if we want to uniquely represent a specific organic compound, we need a chemical formula that shows us how the atoms are actually arranged. And that's where structural formulae come in. A structural formula shows how the atoms in a molecule are arranged by showing what is attached to each carbon atom in turn. Unlike the representations we've looked at so far, structural formulae begin to show us the actual structure of the molecule rather than simply telling us what atoms are present. This means structural formulae can distinguish between compounds that have the same molecular formula but different structures, such as our ethanol and dimethyl ether from before. And that's one of the reasons why they are so important in organic chemistry. In fact, structural formulae are the standard representation used throughout most of organic chemistry. Whenever you're asked to write equations in organic chemistry, you need to remember to use structural formulae rather than molecular formulae. You need to show the exact chemical that's being used or made within that reaction. So what do structural formulae actually look like? Well, here we have ethanol. Its molecular formula is C2H6O, and that tells us that there are 2 carbon atoms, 6 hydrogen atoms, and 1 oxygen atom present. However, the structural formula is written as CH3CH2OH. Structural formulae work by showing what is attached to each carbon atom in turn. The first carbon atom has 3 hydrogen atoms attached to it, so we write CH3. Then we move on to the next carbon atom, which has 2 hydrogen atoms and an OH or hydroxyl group attached to it. When writing structural formulae, you always write the number of hydrogens attached to any particular carbon atom first, so we would then write CH2OH. And this then gives us the structural formula CH3CH2OH. Now let's have a look at another example. Here we have propane. To write the structural formula, we once again work carbon atom by carbon atom along the molecule. The first carbon atom has 3 hydrogen atoms attached to it, so we write CH3. The second carbon atom has 2 hydrogens attached to it, so we write CH2. And the third carbon atom has 3 hydrogen atoms attached to it, so we write CH3. Putting those together gives us CH3, CH2, CH3. Notice that in both examples we've built the structural formula by moving from one carbon atom to the next and describing what is attached to each carbon atom as we go. This carbon by carbon approach is the key to understanding structural formulae. Now, of course, not all organic compounds are going to be simple hydrocarbons. Many contain functional groups, and structural formulae allow us to show those too. For example, let's take a look at ethanoic acid. As always, we start with the first carbon. It has 3 hydrogen atoms attached to it, so we write CH3. The second carbon atom is different. It's bonded to 2 oxygen atoms. One of those is joined by a double bond to the carbon atom, and the other is part of an OH group. When written as a structural formula, this arrangement is represented as COOH, and is actually the functional group of carboxylic acids. Now, we'll look at functional groups in more detail in a subsequent video, but the key thing to recognise is that the presence of this group of atoms in the molecule tells me that this substance is a carboxylic acid, and therefore it tells me how this substance is going to behave chemically. Now let's look at a slightly more challenging example. Up until now, all of our examples have involved straight carbon chains. However, carbon atoms don't always join together in a single line. Sometimes carbon chains branch. Here we have 2-methylpropane. To construct the structural formula, we once again work carbon by carbon through the molecule. The first carbon atom has 3 hydrogen atoms attached to it, so we write CH3. The next carbon atom, however, is bonded to 1 hydrogen and a CH3 group forming a branch. To show this, we write CH. Remember, any hydrogens directly attached to a carbon atom go first. Then, to show that the whole of the CH3 group is attached to this carbon atom, we put it inside of brackets. Then the final carbon atom in our chain has 3 hydrogens attached to it, giving us the structural formula CH3, CH, CH3 in brackets, CH3. And the brackets just tell us that the CH3 group is attached to the carbon atom immediately before it, rather than forming part of the main carbon chain. So as you can see, structural formulae provide significantly more information than molecular, empirical, or general formula. They show us how atoms are arranged within a molecule. They allow us to identify functional groups, and they allow us to distinguish between compounds that share the same molecular formula. Because of this, structural formulae become the standard representation used throughout most of organic chemistry. However, there is still one limitation. While structural formulae show us which atoms are connected together, they don't explicitly show every covalent bond within the molecule. And that leads us to an even more detailed representation. A displayed formula is a more detailed form of a structural formula that shows every atom and every bond within a molecule. In other words, nothing is left out. Every covalent bond is drawn explicitly, and every atom is shown individually. This makes displayed formulae particularly useful when we want to visualize exactly how atoms are bonded together in a structure. Let's start with a simple example, ethane. The molecular formula of ethane is C2H6, and the structural formula would be CH3CH3. But the displayed formula shows every carbon-carbon and carbon-hydrogen bond explicitly. Now let's consider ethanol. Its molecular formula is C2H6O, and its structural formula would be CH3CH2OH. In the displayed formula, we again show every bond explicitly. Each carbon-carbon bond is drawn, each carbon-hydrogen bond is drawn, and the carbon-oxygen and oxygen-hydrogen bonds are shown separately. This makes it very clear that the oxygen is bonded to both the carbon atom and the hydrogen atom, forming the OH functional group present in all alcohols. One of the key advantages of displayed formulae is that they make bonding patterns completely unambiguous. You can immediately see how many bonds each atom is forming and how the atoms are connected in space. Finally, it's important to be aware of a very common exam mistake. When drawing displayed formulae, students often forget to include bonds within functional groups. For example, in an alcohol group, the oxygen must be shown bonded to both the carbon and the hydrogen atom. It's not enough to simply write OH without showing the oxygen-hydrogen bond. Similarly, all carbon-hydrogen bonds must be shown explicitly. Pay particular attention to this when drawing branches or side chains in displayed formulae. Missing these bonds is one of the most common ways to lose marks in organic chemistry questions, and examiners like to include them knowing it will catch some students out. However, this level of detail also makes displayed formulae more time-consuming to draw and more difficult to work with for larger molecules. Because of this, chemists tend to use displayed formulae when they want clarity about bonding, for example when drawing mechanisms, but not when they need to represent large or complex molecules efficiently. This is where skeletal formulae come in. A skeletal formula is a shorthand representation of an organic molecule that is widely used by chemists. Initially, they can look a little intimidating, but they are built from exactly the same structural information we have already been using. Nothing new is being introduced. In fact, we're actually taking information away, but in a controlled and systematic way to make structures quicker to draw and easier to interpret. To understand skeletal formulae properly, we need to understand the rules that govern how they are drawn. First, carbon atoms are not shown explicitly. Instead, each corner or end of a line represents a carbon atom. Second, hydrogen atoms attached to carbon atoms are not shown. They are assumed to be present in order to give each carbon atom 4 bonds. Thirdly, any other atoms that are not part of the hydrocarbon chain or skeleton still need to be shown, alongside the bonds connecting them to the chain. Let's work through a few examples to get to grips with these. Now, you'll need to be able to both draw and interpret skeletal formula. We'll start by looking at how to draw them and then move on to interpreting them after. Let's start with a very simple example, propane. The structural formula of propane is CH3, CH2, CH3. Whenever you're drawing a skeletal formula, I would suggest starting by identifying the longest continuous carbon chain in the molecule. This will then form the backbone or skeleton of your skeletal formula. So in propane, our longest carbon chain is 3 carbon atoms, so this will form the basis of my skeletal formula. As a reminder, when drawing skeletal formula, we don't write any carbon or hydrogen atoms. Instead, we draw a zigzag line representing the carbon-carbon bonds, with each point or end of the zigzag representing a carbon atom. So as soon as I put my pen to paper to start drawing a zigzag line, that counts as the first carbon atom. I then continue my line upwards until I reach the peak of my zigzag. This becomes my second carbon atom, and then I continue down until I reach the trough of my zigzag, becoming my third carbon atom. And that's all I need for propane. I don't draw any of the hydrogen atoms on. Each carbon is assumed to have the correct number of hydrogens attached to it so that each carbon atom is making 4 bonds in total. Now let's consider a molecule with a functional group, propan-1-ol. The structural formula is CH3, CH2, CH2OH. Same process as before. What's the longest carbon chain? Well, it's 3 carbons. So pen to paper is 1, going up to my peak is 2, and down to my trough is 3. And that's the CH3 and both CH2s represented, but we still need to show the OH group attached to the carbon on the right. And this is where a lot of students will make a mistake. If I just wrote the OH group right here, where I finished my zigzag line, I would have drawn ethanol, not propanol, as I would only be saying I have 2 carbon atoms bonded to an OH group, not the 3 carbon atoms I should have. So once I have the zigzag for the carbon chain drawn, I then need to draw the bond that attaches the OH group to the carbon chain, still following my zigzag structure overall. I've now got 3 points of a zigzag line representing the 3 carbon atoms with the bonds between them shown, as well as then showing the OH group and importantly the bond that joins it to the carbon chain. And this is the mistake students make. They forget to show bonds that join functional groups or other atoms to the main chain. Okay, so what about double bonds? Well, here I've got propene, and its structural formula is CH2CH3. To start with, I follow the exact same process. The longest chain is 3 carbons long, so pen to paper is 1, zigzag line up is 2, and zigzag line down is 3. Now that I've got the right number of carbons, I can add in my second bond between the first and second carbon atom, and I literally just draw a second bond alongside the first one that's already been shown. Next up, branches or side chains. And we'll use 2-bromo-3-methyl-pentane as the example. Now don't worry about the name at this point, we'll cover naming organic molecules in another video. It's just here as an example. So once again, I look for my longest carbon chain. Now for this example, there are actually 2 possibilities. The straight chain as it's shown with 5 carbon atoms, or the one with a turn in it with only 4 carbon atoms. I want the longest one, so we'll go with the straight 5 carbon chain. Just as before, I draw my zigzag line. Pen to paper is 1, up to 2, down to 3, up to 4, and then down to 5. Now I just need to look at what's attached where to that 5 carbon chain. On the second carbon along, I have a bromine atom. As the zigzag line is pointing upwards, I draw a line up from that second carbon and add the bromine atom at the end. Remember, the line is showing the bond attaching the bromine to the carbon chain. On the third carbon along, I have a CH3 or methyl group. In this case, the zigzag line is pointing down, so I'll draw my line going down. Now the key thing to remember here is that I don't show carbon or hydrogen atoms that are part of the main carbon skeleton. The line down represents the bond attaching the methyl group to the carbon chain, but the end of the line itself is representing the carbon atom with the 3 hydrogen atoms joined to it. Now that we've got an understanding of how to draw skeletal formulae, let's take a look at interpreting them. So here's my skeletal formula. The first thing I'm going to do is go along the main skeleton backbone and count how many carbon atoms are represented. So here I have 1, 2, 3 carbons. The final end of the line on the right isn't a carbon atom as it's showing the bond to an OH group. So I can now draw out my 3 carbon atoms joined together by single bonds. And now I can have a look at what else is attached to the main chain. On the second carbon, there's a straight line going up. This tells me there's a methyl group, or CH3, attached to that second carbon along the chain. So I can just add this onto my displayed formula. Then, at the very end on the right, I have my OH functional group, so again I can add that onto my last carbon atom. Finally, I can go along my molecule, adding in any necessary hydrogen atoms to ensure that each carbon atom is making 4 bonds in total. And there I have my final displayed formula, and if I wanted, I could then convert this into a structural formula. And then for our final example, same as before, count the carbon atoms along the chain. 1, 2, 3, 4. Draw the stem of my displayed formula with those 4 carbon atoms connected by single bonds. Now I can look at what else is joined to that chain. Well, on the second carbon, I have an oxygen atom joined by a double bond, so I can just add this onto my displayed formula. Finally, I have a methyl or CH3 group attached to the third carbon atom. Again, I can just add this onto my displayed formula. Last step, go along each carbon atom, adding hydrogens to ensure that each carbon atom is making 4 bonds. And this is where you need to be careful. Don't assume you need to add a hydrogen above and below every carbon. I don't need to add any hydrogens to my second carbon here, as it's already making 4 bonds. Don't let yourself get carried away and drop silly marks. So let's return to the question we started with. Why do organic chemists need so many different ways of representing compounds? Well, the answer is that different representations provide different amounts of information. Some are quick and simple, some show detailed structural information, and some allow chemists to communicate complex molecules efficiently. In the next lesson, we'll explore homologous series and see how chemists group compounds together based upon their structures and functional groups. And if you'd like to continue with the course, the full Introduction to Organic Chemistry playlist is on the screen now.